Earth's magnetic field, just like compass needles. With millions of tiny magnets all pointing in the same general direction, the pot itself becomes slightly magnetic. Once it has cooled, the magnetism is locked in.
So if we take an ancient pot like this one, which is from Peru, when it cooled for the first time, it cooled in the Earth's ancient magnetic field, and it became magnetized in that field. And of course, if the field's very strong, then the pot's strongly magnetized, and if the field's very weak, then the pot's weakly magnetized.
By examining pottery from prehistory to modern times, John has discovered just how dramatically the field has changed in the last few centuries.
When we plot the results from the ceramics, this is what we see. Gentle changes as we come forward in time over 12,000 years, a gentle rise, and then a rapid fall as we come towards the present day. The rate of change is higher over the last 300 years than it has been for any time in the past 5,000. It's going from a strong field down to a weak field, and it's doing it very quickly.
In 300 years, the field has fallen 10%, and the rate of decline is increasing. In just a few centuries, it could be gone altogether. So, is the Earth going the way of Mars? There's only one place to look for an answer: the inaccessible region where the field is generated, the Earth's core.
There's a deep, molten heart where these strange attractions start.
But with no way to get to the core, Professor Dan Lathrop is playing with fire as he and his students try to build it in their lab.
Yes, that heater wiring looks pretty good.
They want to find out just what keeps the magnetic field going and what might cause it to disappear.
Trying to test out the new Ohio Semitronics probe.
They model the liquid metal core with sodium because it's highly conductive and much easier to melt than iron.
Sodium actually at room temperature is really a very soft metal. It's sort of cheesy. Of course, when we heat it up to around the boiling point of water, then it becomes liquid, and that's where we actually run the experiments. But it certainly is a hazard in the lab. If we put sodium down into some water, you get little explosions and burning coming off of it.
What you're looking at here is a sphere which contains about 110 kilograms of sodium. When we run an experiment, we'll start spinning this ball like the Earth is spinning and make measurements of magnetic field that it generates on its own.
What they're trying to create is a self-sustaining electromagnetic dynamo, because that's what they think the Earth is. Scientists have a theory about how the core generates the magnetic field. It's based on the close relationship of magnetism to electricity. In particular, the fact that electric currents create magnetic fields.
Now, there's no electric current going through the coil to start with. The iron filings just go down like pepper in a pan, but if I turn on the electric current, then you can see the iron filings line up with the magnetic field that's produced by the current in this electric coil. So it's really currents inside the Earth's liquid metal core that we think gives rise to the magnetic field.
But what gives rise to the electric currents? The answer to that is where things get complicated. Scientists believe that just as the electric currents produce the magnetic field, so the magnetic field produces the electric currents. The key is that the liquid metal in the core is in constant motion.
If you take a moving conductor in the presence of a magnetic field, currents get set up inside the conductor.
In the Earth, the moving conductor is 1 billion trillion tons of molten iron, but the effect can be seen in a simple loop of wire connected only to a meter which measures electric currents.
If I move this conductor in the presence of the Earth's magnetic field, then that gives rise to currents. Once you have currents, those give rise to magnetic fields. So it's kind of a curious loop that gets set up in the Earth's core. A little bit of magnetic field couples into the motion of the liquid, gives rise to currents flowing in the core. Those currents cause more magnetic field, which cause more currents, more magnetic field. So it's kind of a feedback loop that can cause the magnetic field to just arise.
If it works in the Earth's core, it should work in the lab. Scientists are not quite sure what got the Earth's dynamo started. It may have been stray magnetic fields from the sun. But to get a small-scale version going, Dan uses a powerful magnet.
We apply a large magnetic field onto the sodium flow inside the sphere, and you can get a feel for how strong the magnetic field is. If we, Dan, turn on the magnets, we can actually see how they attract this chain quite strongly. Wipe out any bad credit cards you might have in a hurry.
If the electromagnetic dynamo theory is right, then the field generated by their miniature core will be stronger than the field they started with, the magnetism rapidly growing by drawing energy from the motion of the liquid sodium conductor. It's something they haven't yet achieved, but already they have revealed a crucial clue to what might cause a planet's magnetic field to fail.
Well, the different experiments that have been run have shown that a moving liquid metal is critical to getting the magnetic field to arise.
So, if the core were ever to cool to the point where the liquid iron solidified and stopped moving, the dynamo would shut down. This may be why Mars lost its magnetic field so early in its history.
Because Mars is a smaller planet, it will have cooled more quickly than the Earth. So there's a very good chance that Mars has simply become too cold to sustain an active dynamo. It could be that the liquid metal core just froze out at some point.
But will what happened to Mars eventually happen to the Earth?
The Earth's core is very slowly cooling at the rate of perhaps 100 degrees per billion years. So eventually, the whole of the core will freeze. At that point, the dynamo will die.
But scientists calculate that the cooling of the Earth's core is so slow that that point lies billions of years in the future.
The Earth's magnetic field has been around for a long time, at least 2 billion years. It has lasted so long because it has a very large energy source in the original heat that the Earth's core inherited when it was formed. And so the Earth can sustain the magnetic field for billions and billions of years of time.
What's more, the history of the field's decline revealed by the pottery record just doesn't fit the idea that the Earth's internal dynamo is shutting down. Surprisingly, the Earth's field is fading too quickly.
If we were to shut down the heat flux in the core, it would take hundreds of thousands of years, perhaps millions of years, for the field to decrease. And that's not what we see. We see a field decrease which is much faster than that, so there's something else going on in the case of the Earth.
But what? Searching for clues to what's happening deep inside our planet, scientists have turned their attention to a chain of volcanic islands in the middle of the Pacific. Here, there's a record of the Earth's magnetic field that stretches back millions of years. A record not of gradual decline, but of a series of spectacular magnetic upheavals.